Hello friends, Dr. Anuradha from Kekewag Institute of Engineering Education and Research Nasik welcomes you in virtual classroom of subject Engineering Physics for studying topic interference. Today's area of focus is correlation of interference with real life examples, specifically anti-reflection coating. Some of the learnings of learning objectives of today's lecture are to understand meaning of interference with respect to real life examples, to study interference in various types of thin film, to analyze difference in interference pattern due to parallel sided thin film and wedge shaped thin film, to apply this interference phenomena in parallel sided thin film as anti-reflection coating and to distinguish images between optical devices with and without anti-reflection coating, that is ARC, commonly called as ARC. To apply these anti-reflection coating conditions for designing of various materials and various anti-reflection coatings. So with respect to these learning objectives, we are moving ahead with the concept of interference. When we deal with the concept of interference, it means a dictionary meaning is to come in the path of other, or scientific meaning is the superposition of two or more waves arriving at a point simultaneously. This interference can occur between the trans transverse wave or longitudinal waves. There are two types of commonly of interference, that is constructive and destructive interference. Constructive interference and destructive combinedly can be used in various technical application, and destructive doesn't mean that it is of no use, but one of the specific application of destructive interference is today's area of focus is the anti-reflection coating. Anti means against, reflection, and it is a coating. Anti meaning of anti-reflection coating is the coating against or which avoids reflection. It is application of interference in thin film. Now, what is this thin film? Thin film means a thin layer whose thickness is very small, which is coated on some substrate, and due to that coating, here what we are observing, that coating produces destructive interference and it avoids reflection. Now, what is purpose of this anti-reflection coating? Just one of the example I have shown here. The glass is kept between these two fingers and we can see the image of the glass. Now, what happened here in these two fingers? We cannot observe image of the glass. The reason that the glass between two fingers has high transparency. Why transparency is there? Because reflection has been avoided. How reflection has been avoided? Because this glass is coated with anti-reflective material. Various materials for anti-reflection that in further lecture we are going to study. So this glass is coated with anti-reflective material, or it is coated with anti-reflection coating ARC. That coating is also called as thin film and which produces destructive interference. So this concept of anti-reflection coating with respect to application of interference in thin film, today we have to study in this lecture. Another application like radio interferometry are also the applications of interference, but this application is not the focus of today's lecture. Some of the real life examples of thin film which produces interference pattern. Here we can observe interference pattern or, or multicolor pattern due to oil spreaded on water. Multicolor we are observing on soap bubble. We are observing beautiful colors of peacock feather. What is the reason? The only reason is interference in thin film. Who here function as a thin film? In the first case, oil layer acts as a thin film. Here, in the second case, soap bubble itself acts as a thin film. On peacock feather, oxide layer is there, which acts as a thin film. And due to this thin film, we are observing the magical colors, colorful pictures we are observing, and they are nothing but the examples of interference in our real life situation. Some of the lab examples or practical examples with respect to interference. So, just remember the childhood game when you are sitting at the side of pond and you put two stones inside the pond. Water was initially steady, and after putting the stone, the waves are generated, and these waves are getting into the path of each other, and we are observing here the beautiful interference pattern. The same pattern, just similar to the stones in a water pond, you can observe with the help of light rays. Here is one source of light wave, another source of light wave. Of course, interference nothing but one or two or more waves coming in the path of other. So here the light wave originated from one source and light wave originated from other source. Both of they are coming in the path of other and they are getting interfered. So as they are getting interfere, they are producing some pattern. The pattern is in the form of bright ring, bright belt or dark belt. Here some multicolor belt also here we are observing. Here also multicolor bright and dark belts we are observing. And there is nothing but redistribution of intensity, that is interference. Redistribution of intensity or energy or amplitude is nothing but interference, and that redistribution causes alternate dark bright belts. So these belts can be observed with another type of interference, and that interference can be observed in a thin film. Means some of the examples just now we discussed about real life. Now few more real life and as well as practical examples we have to discuss, and these real life and practical examples are with respect to the case of thin film. Now what is thin film? Practically or technical definition says that it's a very thin layer of any material, maybe solid, liquid or gas, whose thickness lies in the range of visible light wavelength. Means how much? Near about 0.55 micron, very small. You can means just close to your eyes visibility. So such a very small thickness thin layer. When light falls on this thin layer, what may happen? It produces such a pattern, alternate dark bright belts. How it produces dark bright belts, that depends on some mathematical conditions given over here. But there are again two types of thin film. One is parallel sided thin film, means thickness of this thin film remains constant, while second thin film is wedge-shaped thin film. Means what? Thickness of this thin film goes on increasing. At the point of contact, thickness remains zero, and with increasing, with moving to away towards the from point of contact, thickness goes on increasing. At the point of contact, some angle has been formed, and that angle is called as wedge angle alpha. So depending on this wedge angle, refractive index mu and thickness of thin film, the conditions are being followed. You will be able to observe the bright belt depending on order, second refractive index, third one is the thickness of thin film, and fourth one is the angle of refraction. And if it is wedge shaped thin film, then one more factor is added, that is called as wedge angle. So mathematical condition for constructive interference, this bright belt will be observed only when this condition is being satisfied. It is twice mu t cos r subject to alpha for wedge shaped thin film is equal to integral multiple of wavelength. While destructive interference will be observed when this twice mu t cos r plus alpha is equal to odd integral multiple of half wavelength. So interference pattern due to one more type of thin film, that wedge shaped thin film is a concentric wedge shaped thin. What do you mean by concentric? Means one point will remain as a center, and then in all direction the wedge shape will be observed. Means what? The thickness of the thin layer increases in all direction, and for that purpose the special device you have to use here is a plain glass plate on which plano-convex lens is kept. When this plano-convex lens is kept, here is the point of contact. At point of contact, thickness of the thin film is zero, and with moving away from point of contact in all direction now, thickness goes on increasing, and hence such a thin layer whose thickness increases in all direction is called as concentric wedge-shaped thin film. In concentric wedge-shaped thin film, instead of alternate dark bright belts, we are observing ring type alternate dark bright rings pattern as an interference pattern. If you change source of light, then if source is neon lamp, then red color bright rings are being observed. If source is white light source, non-monochromatic white light source, then here we are observing multicolor. Particularly for technical application, practical purpose, A sodium vapor lamp is used as source of light, and such rings are called as initially observed by scientist Newton, and hence these rings are this pattern is called as Newton's rings. These Newton's rings are nothing but the interference pattern due to concentric wedge-shaped thin film. The difference in this pattern in and earlier pattern is that only the change in source of lamp. Red color neon lamp, here orange color sodium vapor lamp. Now what we are observing in this pattern, central spot always remains as a dark spot because at this central spot is coming as a result of thickness of thin film, that is at point of contact it is 0. Now when you move away from this point of contact in outward direction, then the spacing between rings goes on decreasing. What we are speaking here, spacing between rings goes on decreasing. So this is the case of, these are the three different cases of thin film which produces interference pattern. How the interference pattern is being observed, that one of the example of uniform thickness or parallel sided thickness we are going to study, and that case is nothing but the anti-reflection coating. Anti-reflection coating is one of the important application of interference in thin film. Now, where this application is being observed in our routine life, one of the best example, our regular glasses. Just one glass of the specs has been coated with anti-reflection coating. Another glass is not having any anti-reflection coating. So immediately you can observe the difference in the image observed with respect to these two glasses. One image is very clear, another one is blur, and the reason that it is not coated with anti-reflection coating. Same thing can be observed, means all these are the optical devices. Another optical device is a camera. This camera not coated with anti-reflection coating, and hence here we are observing blur image. This is the camera lens which is coated with anti-reflection coating. Of course, if anti-reflection coating is given, here you cannot observe that glass also. Here we can observe the glass. And hence the image which the wonderful and the beautiful image we can observe, the colorful image we can observe, clear image we can observe when the lens is coated with anti-reflection coating. If it is not coated with anti-reflection coating, the image is very blurred. The beauty of the picture is getting destroyed. Now, why this solar cells is kept over here? The reason, the solar cells are also using anti-reflection coating. And one of the reason behind that, what is the purpose of solar cell? It converts light energy into electrical energy. Means more the light energy, more electrical energy will be produced. But if the solar cell is not coated with anti-reflection coating, ARC, then what will happen? If it is not coated, then the maximum light which is falling on, or near about 15 to 20% light which is falling on the solar cell will be reflected back. And as it is reflected back, the light will not be utilized, and hence efficiencies of solar cell will get reduced. So how the structure of this anti-reflection coating on solar cell is there? This is your structure of silicon solar cell. The core material silicon with p-type doped silicon, lightly doped silicon. Then next layer is n-type heavily doped silicon. Then further layer, this green color or bottom blue color, both of these are the metal contacts for conduction of electricity. And the topmost layer given here is a silicon nitride anti-reflection coating. Here we have to focus on ARC, that is anti-reflection coating. And the reason for this anti-reflection coating is that anti-reflection coating does not reflect light which is falling on it. Maximum light is coming towards this junction region or n-type and p-type region. This n-type and p-type region will absorb the light and will convert it into electricity. Otherwise, reflection will cause reduction in intensity of light. Here you can observe this is a natural color of solar cell is a gray color, but when it is coated with anti-reflection coating, the dark blue means depending on the color of anti-reflection coating, dark blue or dark uh, gray color we can observe for anti-reflection coating. The images of solar cell with and without anti-reflection coatings are also shown over here. Hence, the anti-reflection coating is a major layer or a very important factor in optical devices or even in solar cell. Optical devices like specs or camera or telescope lenses, or here in solar cell for increasing their conversion efficiency. Now, technically, just have an overlook how the physics lies between anti-reflection coating. Of course, it's a layer. We can observe beautiful pictures with the help of anti-reflection coating, but how this anti-reflection coating is working. So just let us have an imaginary diagram that this is a camera lens and which is coated with this yellow color anti-reflection coating made up from magnesium fluoride material. Means various material can be used. Magnesium fluoride can be one of the material for camera lenses. Silicon nitride can be one of the anti-reflection coating material for solar cell. So here camera lens is coated with anti-reflection coating of magnesium fluoride. Now thickness of this layer is taken in such a way that its optical path is lambda upon 4. What is the lambda here? Lambda, how it is selected? It is 5500 angstrom, the wavelength of light, which is most sensitive to human eye. Lambda is selected as a middle region of the visible light. Now camera lens is generally made up from glass with refractive index 1.5. Now, how this magnesium fluoride or why it is selected? Because it is having refractive index 1.38. Simultaneously here, the light has to travel initially traveling from air with refractive index 1, then magnesium fluoride with refractive index 1.38, and then glass with refractive index 1.5. Means refractive index from top to lower order is goes on increasing. And this is the one of the condition for manufacturing of anti-reflection coating. The first condition that refractive index of air should be less, then the anti-reflection coating should be having little higher refractive index, which should be lower than glass and should be higher than air. Now how this anti-reflection coating works? When light falls on the anti-reflection coating, then here at the surface partially it is reflected as ray 1, then partially it is refracted inside this anti-reflection coating. At the bottom edge of anti-reflection coating, there is also reflection. And again, here we are observing refraction as ray. Now, for anti-reflection coating, ray 1 and ray 2 are the major parts. We are not speaking here transmitted rays. We are not going to look after them because we have to reduce the effect of reflected rays. And to reduce that effect, we have to produce destructive interference between ray 1 and ray 2. And to produce destructive interference between these two rays, what is essential? That these rays should follow condition for destructive interference. And the condition for destructive interference will be followed only when the phase condition, that is optical thickness of anti-reflection coating, that is mu t, optical thickness means mu t, is equal to quarter of wavelength, means this thickness is lambda by 4 is the second condition for manufacturing of an anti-reflection coating. Now how part difference is destructive follows condition for destructive interference? Just look. Uh, till the ray 1 travels some distance in air, the ray 2 has to travel distance lambda by 4 plus lambda by 4. This lambda by 4 plus lambda by 4. Then secondly, here is the path change of lambda by 2 as per Stokes law, and here at this bottom also the path change of lambda by 2. Why? Because this is also the denser medium and this one is also denser medium, and hence path change or phase change of lambda by 2 is observed in ray 1 and at the bottom of the anti-reflection coating. So lambda by 4 plus lambda by 4, lambda by 4 for this distance, lambda by 4 this one, lambda by 2 at this path change, lambda by 2 at this path change at bottom of thin film, and hence the total optical path difference in between ray 1 and ray 2 is 3 of lambda by 2. This is nothing but the path difference is the odd integral multiple of half wavelength, and the condition for destructive interference is being followed. What it indicates? That there is no light in reflected system. When thickness of this anti-reflection coating is maintained as lambda by 4 mu, or optical thickness is lambda by 4, and refractive index of the material selected for anti-reflection coating lies as the square root of the refractive index of glass, then only this coating will produce condition for destructive interference, and we will be able to observe no light in reflected system. All the light which is falling on this anti-reflection coating will be transmitted towards glass, and we will be able to observe clear image with the help of anti-reflection coating. So this is the theory lying behind anti-reflection coating. Now we have to focus on the practical example, whether which material will be applicable as anti-reflection coating. If it is applicable, then how much thickness should be maintained. So one of the example, can thin film of water formed on glass window pane act as anti-reflection coating? If yes, then how much should be its thickness? So just with respect to this diagram, this is a incident right having wavelength 5500 angstrom. Now anti-reflection coating material used here is water with refractive index 1.33 given here. Now camera lens is made up from glass with refractive index 1.55. Now what we have to solve? Whether this water will act as an anti-reflection coating. Yes. Why? The amplitude condition, that is refractive index of water, is less than refractive index of glass, and hence it works as anti-reflection coating on glass. Now second thing, what is its thickness? The second, how should be its if a thick layer of water, it will not survive. Hence, thin layer of water only will survive as anti-reflection coating. And hence, the second condition, phase condition, T is equal to lambda by 4 mu, that is lambda is 5500 angstrom upon 4 into mu as 1.33 gives you the answer 1034 angstrom or zero point 0.1 micron. A thin layer of 0.1 micron of water when spreaded on glass or window pane, then it will act as anti-reflection coating. So here is one of the practical example, and then with the help of this example, easily you can imagine that which material can function as anti-reflection coating. Some of the examples, practical examples of anti-reflection coating we discussed in this lecture. In this lecture, we started with definition of interference. We started with types of interference. Then we covered up various types of thin film in which how will be the interference pattern can be observed, and what are the conditions for interference, constructive interference and destructive interference. Similarly, one type of thin film interference is a uniform thickness thin film, that is parallel sided thin film, and application for that is anti-reflection coating. So thanks for your passionate listening of this video. If you like it, then please subscribe. Welcome you in next series of interference lectures, interference videos. Thank you.